To get access to the Network Plus notes as well as the mock exams and the practice question slides, join the Hackaholics Anonymous community. If you join as a cyber agent, cyber guardian, or cyber master, you'll get access to all of the notes, the mock exams, and practice question slides, as well as many other perks that are available to Hackaholics Anonymous members like Python automations and exclusive content, as well as monthly live streams with me. And to join, you can click the link in the description below, or you can go to our homepage and click the join button there, or you can simply go to youtube.com/@HankHacksHackers/join, and you'll be able to join Hackaholics Anonymous. Now let's get back to the Network Plus training. All right, so up until this point, everything that we've talked about has been more conceptual and theoretical. And I guess we will still be talking in theory and concepts, but the overall purpose of this particular chapter is the implementation of everything that we've actually been talking about. So as the name implies, literally we are going to be talking about how to implement, how to apply these various strategies and tactics and concepts and theories and everything that we've covered so far, and how they actually apply to real world scenarios, more so than what we've been doing with the end of each section. We talk about the real world scenarios. This is I guess the implementation of it. It's really the best way that I can say it. So the first portion of this is the routing technology. So as we've already discussed so far, the routing of traffic is done through specifically the router. It's done on the network level and or the network layer, and it goes through the various potential devices that we have, which is the actual router, the switches, so on and so forth. So there's a variety of routing technologies that we've already discussed, and they are essential for directing data packets between networks. So when you think of routing and routers, think of the communication between various local area networks, wide area networks, and routing technologies determine the best path for a packet delivery, and it ensures the efficient and reliable communication. So understanding static and dynamic routing protocols, address translation methods, and redundancy technologies is very important, and it's as the word implies here, is critical for managing modern networks. So how does data get transferred, right? How is data delivered? The packets themselves, the data packets, how are they delivered? How can you make sure that it gets there as fast as possible, reliably, without affecting the integrity of the data that's being transferred? That's the entire purpose of everything that we're going to be talking about right now. The first thing that we need to talk about are the various routing protocols. There are two main ones. There's the static routing protocol, and then there's going to be a dynamic routing protocol. And dynamic host configuration protocol is something that kind of relates to this, but we are specifically talking about routing itself. So dynamic host configuration has to do with the issuance of addresses, the issuance of IP addresses dynamically. But there is the routing, the actual routes that traffic will take, those data packets will take, and that can be done through these routing protocols. Now, static routing is manual configuration. So it's when an administrator, an IT administrator, a network administrator, manually configures the routes that is available for the routing table, which is the various routes that a given packet will take outside of a network and how it will travel. Essentially, that is what our routing tables are. And the features of static routing are that it does not adapt to network changes automatically. As the name implies, it's static, and of course it's being manually configured. So anytime that there's a change that happens in the network, the administrator has to go ahead and adapt those changes to whatever happened inside of the network. It's suitable for small and simple networks because, as you can imagine, it will take a lot of energy and time and effort to manually configure a bunch of different routes in the routing table for a massive network. So this really only works for a small, simple network because of the fact that everything's being done manually. So static routing is manual. Just keep that in mind. The pros of static routing are that it's predictable and it's secure. There's no dynamic updates. You know exactly what you've done and where everything is and how everything is working until you make the next change. And it is secure because, again, there are no dynamic changes or updates that are being made. There's minimal resource usage because pretty much with the exception of the energy of the administrator, the time of the administrator, there's pretty much no other resource that's actually being used. Once the configurations are done, that's pretty much it. The network is going to operate as it does. The cons are it's labor intensive, right? There's a person that actually has to do this to configure and maintain, especially in larger networks, because there are larger traffic segments, there are larger datagrams, so to speak, that are leaving that network or being imported into the network, and you have to route all of those routes. It's the word is starting to lose meaning, but to route a route, it's a verb and a noun, I think. But to route a route is labor intensive. You actually have to do that manually, as a person has to go ahead and do it. So imagine if it's a massive network and requires multiple routers or dozens of routers. It just becomes really crazy to think about, especially when you go across multiple locations. So you have multiple LANs, multiple local area networks that are inside of a campus, for example. So we'll just keep going back to the Google campus. So the Google campus has like multiple buildings, right? So imagine that we're not even talking about different cities and we're not talking about different countries. We're talking about the same city, same location essentially, but they have this, 10-acre portion of land, and on those 10 acres they have a dozen buildings, and each one of those buildings at the very least has a few routers. So let's say 3 routers per building, at least, I would say. But let's say they have 3 routers per building and they have a dozen buildings, that's 36 routers, and somebody has to manually configure all of those things. It just ends up taking a lot of labor. It ends up taking a lot of time and energy. You cannot handle network failures dynamically because something happens. Now that person or that team of people have to go and try to troubleshoot and figure out what just happened. The use case would be point-to-point links within a single path to the destination. So point-to-point links, as we talked about earlier, is a logical topology that connects various networks together. So with a single path to the destination, that would kind of the point-to-point from one location to another location. That would be the use case for static routing, because for the most part, so long as the locations aren't going to change and you won't need to change your routers or the routes or whatever, it should be fine, right? If you start going into multicast or going into multiple locations where you have to start broadcasting to, and then you have to start managing all the different routes and the routers and all of that, the routing tables that are associated with them, it just becomes really, really labor intensive. So it's designed for either small networks or these point-to-point going from one LAN to another LAN type of a thing, as long as it's simple and fairly small, quote unquote, it should be easy to manage. Dynamic routing, on the other hand, is automatic. So dynamic routing protocols automatically update the routing table based on the changes in the network topology. The open shortest path first is something that we've already discussed. So this is one of the key protocols, and it's a link state protocol, and it calculates the shortest path using oh my god, I'm going to destroy this. I'm not going to be able to pronounce this. Dijkstra, we'll just call it that. This algorithm, it's you can't the pronunciation I'm probably going to murder, but you can't not recognize that. Once you see that, you will know that this has to do with the open shortest path first. So OSPF, open shortest path first, is the protocol. It's a link state protocol that calculates the shortest path using this specific algorithm, Dijkstra algorithm or Dijkstra algorithm. It divides large networks into smaller areas or segments for scalability, and the use case would be an enterprise network that requires fast convergence. Then we have the border gateway control, which is a path vector protocol. And the features of this that manages the routing between autonomous systems and determines the best path based on policies and attributes like the AS path and the autonomous system's path, and then the next hop. So it determines the best path based on policies and attributes like the autonomous system and the next hop. The next hop from one route to another router, that's what's considered a hop. Anytime that the traffic packet or the frame or the we can call it the segment and the datagram, because that's essentially the data. Once it gets to like level 7, we're talking about data. Level 7, 6, and 5, we're talking about data as the unit of measure. And then prior to that, we're talking about segments, and we're talking about datagrams. So when you consider where these things are going to start routing, when it goes to the on the router level, we're talking about the actual packets themselves. And so it's the best path that a packet can take. And each hop that that packet takes to get to its location, it can take up to a maximum of 30 hops, according when we run traceroute commands to try to see how many hops it actually took. And we'll get to see that it'll go from one router to another one, to another one, to another one, and it'll go to the actual router of the internet service provider, and it'll go to its final location and end up at the destination that it needs to end up at. And each one of those hops is when it goes from one router to the next one. So trying to determine the best path based on whatever the policies and attributes are, for example, the autonomous system itself or the next hop. And again, it's supposed to take the shortest path. Even in this particular case, it still should take the shortest and the fastest path. So this is what the shortest path first is, and then this is what border gateway control is. Now I want to give you a little bit more information about the link state and the path vector protocols. So the link state protocol is a routing protocol that allows routers to determine the best path between network nodes by sharing information about the network topology. And this is also known as the shortest path first protocol. So we've already talked about this. So the initialization is a router discovers nearby routers and establishes communication. The link state advertisement, also known as the LSA, is when the router creates a packet about the state of its links and then sends it to all of the other routers in the network. And then each router builds a network database based on the link state advertisements that it receives, and then the shortest path is then calculated. The routers use algorithms like the Dijkstra to find the shortest path to each destination. So this is what the link state protocol is like, and this is how the establishment of the shortest path is done. So first there's the router that discovers nearby routers and establishes communication with them, and then the link state advertisement is created. So the router creates a packet about the state of its links and then sends it to all of the other routers in the network, and then each router builds a network database based on the link states that it receives, the link state advertisements that it receives, and then based on its database that it has, based on that table that it has, then it can determine which one is the shortest path that it can possibly take, and then it uses algorithms like the Dijkstra to be able to find that shortest path. So this is what our link state protocol is. Now, the path vector protocol is a type of network routing protocol where the nodes exchange information about their entire path to a destination, including the distance, so allowing for better loop detection and more efficient routing compared to standard distance vector protocols. And the most prominent example of path vector protocol is the border gateway protocol that we just discussed. Now, the key points about this is that unlike basic distance vector protocols, which only share the distance metrics, path vector protocols share the complete list of autonomous systems and a route that the route passes through. So they share the complete list of all of the systems that the route actually passes through, and that enables the detailed route analysis. And then by knowing the entire path, a node can easily identify and discard routing updates that will create loops in the network. And then the path vector protocols often allow for complex routing policies to be implemented based on the automated system's path, or the autonomous system's path information. So the border gateway protocol, which is widely used for inter-domain routing on the internet, and this is just one of the examples of this. So unlike the example that we saw over here, where the protocol creates these database of these LSAs, these link state advertisements, once it creates that database based on those LSAs, then it can use algorithms like this to find the shortest path. And the border gateway protocol gets the entire path. Because it knows the entire path, the node can easily identify and discard routing tables that would create loops in the network, or it can create the shortest length, or detect the shortest length, by knowing the entire path. So it shares the distance metrics, and then the path vector protocol share the complete list of those autonomous systems that the route actually passes through, and then that enables the detailed route analysis. So really, essentially, the path vector protocol is just telling us exactly what the border gateway protocol itself did, and then same thing with the link state protocol. So these definitions that we have over here, they're essentially just lengthier versions than what we had in our notes, but I just wanted you to get the definition of what these actual protocols are, because this is saying that the open shortest path first is this type of protocol, and I just want you to know what that is. And that happens when these link state advertisements are sent out by these routers, and then an entire database of these routers are created, and then based on that database, the protocol will decide, using something like the Dijkstra algorithm, it'll decide which route it's going to take and what the shortest path is going to be. And the border gateway protocol is a type of path vector protocol, and based on that, it has this massive database. It has the entire path. It has the entire path established already. It knows what the map of the entire path looks like and what all of these autonomous systems looks like, and from there it'll determine the best path based on those policies that are generated for it or configured for it. For example, the automated systems path or the next hop. We do have a couple of other dynamic protocols as well. So we have the RIP, which is the Routing Information Protocol, the Distance Vector Protocol, simple but slow convergence. So this is what this is. It is a distance-based, so distance vector protocol. It's simple, but it has slow convergence. And then we have the EIGRP, the Enhanced Interior Gateway Routing Protocol, and it's a Cisco's proprietary hybrid protocol. So these are other dynamic routing protocols that are available. And the pros and cons of dynamic routing would be that, it adapts to network changes automatically. It scales well for large complex networks, but the cons are that it requires more CPU and memory resources because it's going to be operating automatically and adapting in real time dynamically. And it is susceptible to routing loops if it's not configured properly. So one of the things about the border gateway protocol that we saw was that it solves for the loops of routing because it actually has the entire map of the routing paths that a packet could take, that data could take. So that's why the border gateway protocol is one of the most commonly used protocols of that path vector. Okay, so let's move on. Now, another concept that we need to talk about when it comes down to routing is the address translation, the concept of address translation. So network address translation is one of these very common protocols that you're going to hear about regularly, and it actually is very useful in security as well. And what it does is that it maps private IP address to a single public IP address that allows multiple devices to access the internet without their private IP address being displayed to the entire world. So it translates the addresses of the network, right? So it takes private IP addresses, it can map multiple addresses to a single public IP address, and it allows multiple devices to be able to access the internet. So you have the static NAT, which is a one-to-one mapping of private to public IPs. You have the dynamic NAT, which maps private IPs to a pool of public IPs. And then we have the overloading, which is a PAT as well, that uses port numbers to allow multiple private IPs to share a single public IP. So these are the types of network address translation, and the benefits would be that it conserves IPv4 addresses. This is one of the big things that is allowing for IPv4 addresses to still be in circulation and to still be relevant and in use, is that because there is network address translation taking place, it actually conserves IPv4 addresses, because for each individual private network, there's a set of, let's say, public IP addresses that are being reused across the globe. And for a lack of a better word, it just translates all of those private IPs to public IP addresses that are not being used by other, they are being used. I should be saying it like this. these private IP addresses are technically probably being used by other devices in other countries, but for the given country that it's issued to, for the device that is inside of that given country, it's going to be translated into a public IP address so that as it communicates with global machines across different countries, these IP addresses won't clash, right? And they won't say, okay, it's coming from the same IP going to the same IP, because technically it would be the same IP, because again, it's limited, right? It has a little bit over 4 billion variations. So there are way more than 4 billion devices. So what happens is that those same private IP addresses that could be inside the United States, they get translated so that when they reach the ones that are in Europe or in, I don't know, Bangladesh or something, or in South Africa, whatever it is, once they reach these other countries, it could technically be the same private IP address that also exists in South Africa. It's just that it's been translated on its way out. And once it reaches over there, it looks like there are two different IP addresses communicating with each other. Sorry, I probably made that a little bit more complicated than I should have. But the benefit is that it does conserve IPv4 addresses. That's kind of the big benefit. I think I overcomplicated that explanation, but hopefully you understand what's going on. It also adds a layer of privacy by masking internal IP addresses, which is a really important element for security. And the use case would be small businesses connecting to the internet using a single public IP address, which again allows for the conservation of IPv4 addresses. So you could technically have a dozen private IP addresses that are inside of the business, but then once they connect to the internet, they connect with one public IP address. Therefore, it conserves the IP addresses that are actually communicating across the internet at large. Hopefully that was a little bit simpler of an explanation. And now we get to the concept of redundancy technologies. So redundancies are a big deal in pretty much every part of IT. And as long as you understand what a redundancy just by itself is, if something is redundant, right? So if something is redundant, it means it's technically not necessary, but it serves as a fallback. It serves as a secondary measure, as a contingency, right? So that's what the concept of a redundancy is. So when we talk about it in networking, there's a variety of different ways that you can have redundancies. We've already talked about multiples of them. So you could have redundant servers, right? So if one server crashes and goes down, a backup server kicks in and it has the same function, it has the same data, and it's just sitting there just in case the first one goes down so that the service overall doesn't go out of service, like the service doesn't crash, right? So the first hop redundancy protocol, FHRP, the first hop redundancy protocol, ensures network availability by automatically rerouting traffic to a backup gateway if the primary gateway fails. Literally the same definition as any other type of redundancy, except now we're just talking about the hop itself, the actual routing of the traffic packets themselves. So the first hop redundancy protocol ensures that the network is available by automatically rerouting traffic to a backup gateway if the primary gateway fails. So common first hop redundancy protocols would be the hot standby router protocol. It's a Cisco proprietary protocol, and it provides a single virtual IP address and assigns one active and one standby router. Okay, so you have, this is the backup gateways that we're talking about here are the backup routers. So in case the primary one fails, there's a backup router that actually acts as that gateway, and then it then starts to route the traffic. So the hot standby router protocol, HSRP, is a Cisco proprietary protocol that has a single virtual IP address and assigns one active and one standby router. Then we have the virtual router redundancy protocol, which is an open standard equivalent of the hot standby router protocol. Open standard meaning it's open source. It's not proprietary to Cisco machines or Cisco itself. You probably don't have to pay for it because, again, it's an open standard. So you can just use this as the protocol to create your redundancies. And it does the same thing, right? It assigns one active and then one standby router. And then we have the gateway load balancing protocol, which is Cisco proprietary, and it balances traffic across multiple routers simultaneously. And this is load balancing. So this is similar to what we do with load balancers with traffic that's coming into a network, just in case there is a flood of traffic that comes in and we don't want the server to crash. So we use a load balancer to distribute the traffic among multiple servers. Same thing, except now we're doing it across multiple routers so that the traffic does not crash any given router. And if you haven't noticed already, Cisco is a really big name in networking, and they have some of the most powerful technologies, and they have their own command line syntax as well for all of their technologies. And then there's even a certification that is the CCNA certification, the Certified Cisco Network Associate, that is used to essentially qualify somebody for being a really good network administrator, or at least somebody who gets to become a network administrator. And a lot of networking jobs, network admin, network engineer jobs, they require you to have the CCNA certification. And so the next step for you, if you are really interested in pursuing networking, the next step would be to go from Network Plus to CCNA. Another redundancy technology would be the virtual IP, the VIP, an IP address that is not tied to a specific device, but instead floats between devices for redundancy or load balancing. So this could be a web server cluster to balance incoming traffic, or it could be ensuring high availability for critical services. So this is a virtual IP address, right? It's not tied to a specific device, but instead floats between various devices for redundancy or load balancing, just to make sure that these various devices, in case something needs to access them, they can be accessed. And this would fall under dynamic routing. So this cannot be a static routing type of philosophy. And same thing with everything else that we've discussed so far as well with these various redundancy technologies. These are all, they fall under dynamic, because it would be a nightmare to try to do this statically or to try to do this manually, where an administrator or a team of administrators are sitting there and just managing these IP addresses and assigning them to various devices. It would be impossible to do. So these virtual IPs and everything else that we discussed so far are parts of the dynamic routing, and they all fall under redundancy. So these redundant technologies and these redundant machines and these redundant protocols all fall under dynamic routing. So a few real world scenarios here. So scenario one would be that a static route for a point-to-point link needs to be established. So the problem is that the wide area network link requires a simple and direct path. That's the problem. Now we could do a configuration of a static route to define the specific path for packets. So we're talking about static routing, and static routing is best for point-to-point connections of local area networks to establish a wide area network. So if a wide area network link requires a simple direct path, you would use static routing to create that point-to-point connection. Then we have the dynamic routing in an enterprise network that needs to take place. And a network with multiple redundant paths needs fast convergence during link failures. So now we're talking about dynamic routing, and it needs to happen quickly, right? So that's what fast convergence is really. It connects to dynamic routing because there's no person manually doing this, right? So there's a network that has multiple redundant paths and it needs fast convergence during link failure. So you would implement the open shortest path first to dynamically update routes based on network changes, and that would be done for dynamic routing. And then to make sure that in case there's a link failure with any of the routers, there's multiple redundant paths that are available and they are dynamically chosen. Then we have the network address translation overloading in a small business. So the problem would be that a small office has multiple devices but only one public IP address. So you would configure the public address translation to map private IPs to a single public IP with unique port numbers. And my sincerest apologies, it's not public address translation, it's port address translation. My bad. I really honestly, like, no bull, I really thought it was actually port address translation, but for what I think it was like the context of what we were reading that made me automatically say public address translation, and I just had to verify it. So it's port address translation. PAT's port address translation which is a type of network address translation that allows multiple devices on a local network to share a single public IP address by assigning unique port numbers to each device, effectively conserving the limited pool of available IP addresses, and is commonly used in home networks where multiple devices access the internet through a single public IP address. But the way that that happens is that each one of those devices now is using a unique port connected to that public IP address, and that's how it's able to use the same IP address to access the internet. Scenario 4 is the FHRP for gateway redundancy. So the problem would be that there's a primary gateway that fails and disrupting the network's access. So what we need is to use the HSRP or the VRRP to switch traffic to a standby gateway automatically. And the HSRP is the one that is proprietary to Cisco, and then VRRP is the open standard version of it that has that initial primary gateway, that primary router, and then there's a backup router just in case something like this actually happens. And so the primary gateway fails and it disrupts network access. So you would use one of these protocols so that you can switch the traffic automatically to a standby gateway and make sure that you still can process your traffic and have incoming and outgoing traffic. And then finally, we have the VIP for load balancing. And the problem is that a web application experiences high traffic, so we deploy VIP to distribute traffic across multiple web servers. Which brings us to our practice questions for routing technologies. So, which type of routing requires manual configuration by an administrator? Is it static, dynamic, OSPF, or BGP? Now, OSPF and BGP are both parts of the dynamic routing protocol. And so what requires manual configuration by an admin, that would be a static routing. Which dynamic routing protocol is most commonly used for routing between autonomous systems on the internet? So remember, autonomous systems, those ASs, and then that connects us to the routing protocol actually getting an entire map of these ASs. So it would not be RIP, it would not be EIGRP, it is the border gateway protocol, because the open standard open shortest path first is a different type of routing protocol that first gets those advertisements, those link advertisements, right? So BGP would be the one that is used for routing between autonomous systems on the internet. What is the primary benefit of using network address translation? It provides redundancy for network gateways. It allows multiple devices to share a single public IP address. That sounds pretty solid. It ensures faster data transmission over WAN links. It dynamically updates routing tables. And the answer, in my opinion, would be B. Very good. What does a first hop redundancy protocol provide? Faster data packet delivery within a LAN, high availability by ensuring backup gateways, dynamic allocation of IP addresses, load balancing across autonomous systems. So this is not for our load balancing. This is to make sure that we actually have the backup gateway. And this is the first hop redundancy, is the Cisco's proprietary protocol. Which FHRP is an open standard and not vendor specific? So that was the thing that we were talking about. So port address translation is not a part of this conversation. And HSRP is the one that we just discussed that actually has to do with Cisco. I want to say it's the VRRP is the one that's not vendor specific. Very good. Okay, great. I forget what it stands for though. Bonus points, brownie points if you remembered this already. What is the main difference between static network address translation and port address translation? And so static NAT maps multiple private IPs to a single IP, while PAT maps one private IP to one public. And we literally just looked up this definition, so this is not correct. This is probably the inverse of this. This is the vice versa of this, or that's like the opposite of what actually is done. So static NAT is used for private networks, while PAT is used for public networks. Not really. Static NAT maps one private IP to another public IP, while PAT uses port numbers to share a single public IP. That's exactly the answer. There we go. We don't even need to read further. Which protocol uses the Dijkstra algorithm to calculate the shortest path? And that is the open shortest path first. There we go. What is the purpose of a virtual IP, so the VIP? to automatically assign IP addresses in a network, to act as a backup IP address for routers, to allow multiple devices to share an address for redundancy or load balancing. I think that's the one. To encrypt data transmitted between network devices. I'm going to say C. There we go. Which type of NAT dynamically maps private IP address to a pool of public IPs? Is a static NAT? No, because it would, if it's static, that means it's doing it, I think, manually. Somebody's doing it. Dynamic NAT, port address translation, or the virtual IP address. So it's not the virtual IP address. Port address translation maps a pool of IP addresses to a singular public IP. So I don't think that's the one either. I'm going to say it's dynamic NAT. Very good. A company needs to distribute traffic across multiple routers while maintaining gateway redundancy. Which protocol would best meet this need? So a company needs to distribute traffic across multiple routers while maintaining gateway redundancy. Let's see. It's not the open shortest path first. I want to say it's HSRP. I'm going to say HSRP. Let's see if that's the right answer. It is not the right answer. It is the GLBP. And again, I don't remember what these things stand for. I need to get much better at these acronyms. There are so many flippin' acronyms. But okay, so it's GLBP. GLBP is what is used to distribute traffic across multiple routers while maintaining gateway redundancy. So HSRP is the version where there's two routers, and you have your primary and then you have your secondary. So I guess that should not have been the answer. I should have just kind of deleted that by process of elimination. So it would be the GLBP. I definitely know that it's not open shortest path first. I know HSRP is the first one that we saw that was a Cisco proprietary, and it has that primary and then a redundant router. So yeah, all right, GLBP. Oh, and that's it. That was all of the questions that we had for section 2.1 for routing technologies. So now we can actually go talk about switching technologies. To get access to the Network Plus notes, as well as the mock exams and the practice question slides, join the Hackaholics Anonymous community. If you join as a cyber agent, cyber guardian, or cyber master, you'll get access to all of the notes, the mock exams, and practice question slides, as well as many other perks that are available to Hackaholics Anonymous members, like Python automations and exclusive content, as well as monthly live streams with me. And to join, you can click the link in the description below, or you can go to our homepage and click the join button there, or you can simply go to youtube.com/@HankHacksHackers/join, and you'll be able to join Hackaholics Anonymous. Now let's get back to the Network Plus training. Okay, so we already know that routers and routing technologies are used for communicating between various networks, and the way that you can create communications or create segmentations within the same network. We would do it with the switch and switching technologies. Switching technologies are fundamental to modern LANs, so the local area network, which is again the same network. So if we were to look at, and I think I need to find like a good graphic, and I should have probably done this earlier, so I do apologize that this is kind of coming in a little bit later into the training series. But if we compare the sizes of the networks, the LAN is your local area network. It's your actual home, right? So it's probably better if I actually just find the graphic. Again, sorry that this is happening so late, but let me just find a really good visual for this. So this is a big contrast as far as the images are concerned. The local area network in this particular case would be, you have the router here, and then you have all the devices that are connected to the router. So this could literally be your house. It could be somebody's office. And then the wide area network in this particular case is almost like the actual internet itself, because the wide area network, or the internet, is a wide area network. But even if we were to just look at, there's a company, and then for that company, we have this location and then this location, and then through their internet service provider, they are connecting their two networks together. And then this would be one LAN, this would be another LAN, and then those two LANs connected together would be a WAN that belongs to that company. But in this particular case, you have a campus for, let's say, a college, you have an enterprise, which would be a company, you have a government building, and then you have the city. And then this city, right? So all of these buildings in this city, each one of these buildings could be a LAN, and then this city by itself could be a WAN, and then this government building could have multiple routers on the different floors that it has. So the government building could be a WAN, right? So essentially a WAN is just a combination of LANs. And then when you look at it from the really, really big perspective, it's like, okay, well, the internet itself is just a bunch of different LANs that are connected together through their internet service providers. And so when we look at the internet at large, the World Wide Web, the way that we look at that is literally saying that this building has, like it's a skyscraper. So this building probably has a dozen LANs in it, local area networks. That building by itself could technically be a WAN, and then this building, and then this building, and then this building. So this is just one WAN, like one giant WAN. And then this city connected to this city right here through the internet is, again, this is one giant WAN as well. So the wide area network is just a combination of a bunch of different LANs, and the LAN is just as long as there's a router that is connected to either a switch or just the router itself acts as the wireless access point or something like that. But this router just by itself is a local area network, and then the internet has millions of routers. That's basically how we look at it. A wide area network could be 2 LANs, or it could be 1,000,000 LANs, right? That's basically the way that we can consider the difference between a local area network and a wide area network. Now, since we're talking about switching technologies, the switch itself is specific to the local area network. Routers are where the communication of the wide area network comes in. Switches are specific to the local area network. Therefore, when we talk about this particular section where we're saying, okay, now we need to talk about switching technologies and how they connect the local area network, how they are actually fundamental to the local area network, this is where switching comes in. And so switching technologies provide the mechanisms to segment, optimize, and secure network traffic, and understanding a virtual LAN, the VLAN, and then aggregation of links and the spanning tree protocol is all critical for configuring and managing switches effectively. And of course, that's what we're about to talk about right now. Okay, first we need to talk about what a VLAN is. So a virtual local area network, a virtual LAN. And a VLAN is a logical grouping of devices on a network that allows devices to communicate as if they were on the same physical network, even if they are not. And this is typically when you want to split a LAN into segments of different LANs, right? So you would split your one LAN, and then you create logical groupings of devices, and each one of those logical groupings act as if they were on the same physical network, even though they're not. And the way that this is done is through the switch. So if we look at this image right here, you have these red circles, or these various circles that we have over here, acting as individual virtual LANs, so individual LANs themselves, right? So you have this switch device, this gray box that we see right here, and through the switch, essentially each one of these Ethernet cables can be dragged out from the switch. So let's say the switch is sitting inside of the server room, and then from this switch, there's a Ethernet cable that's dragged out, and it goes to a given floor, and then that floor acts as a virtual LAN, and it belongs to the HR department. And then we have this one that's dragged out of the switch, and it goes to a separate floor, and it belongs to the banking department or to the finance department, whatever it is. So it's technically coming from the same router. So the internet service provider AT&T, Spectrum, whatever. They're providing the internet to the building, right? And the internet is being dragged out from the various routers, because technically, like, this could belong to one company and that company is paying the bill for this, and this could belong to another company and the company is paying the bill for this, and then the individual companies would actually have their own switches, and then those switches would drag out the wires to whichever floor or whichever room belongs to that given company. So technically that could be the case, or it could be the case that you have one router that's feeding the traffic into the switch, and then from the switch the service is being split off into various rooms and various floors, and then each one of those rooms and those floors are acting as their own LAN, but they have been logically separated. So they are virtual LANs, because technically the router is the LAN, right? So one router will give you a local area network, and then you need to just split that off into a variety of different departments and rooms and floors and whatever. And when you do that through the use of the switch itself, and then now you create logical separation. So this is technically acting as if its own LAN, except it's logically separated. And even though physically it's part of the same LAN, physically it's you getting its data and its internet service from the same physical router, technically it's thinking that, okay, I'm my own little segment, right? And this is how we can create micro segmentations or virtual LANs, by using switches. So that is how that actually plays out. Now, the key features of a virtual LAN, a virtual local area network, is that the segments traffic, the LAN itself segments traffic to improve security and performance. So it segments traffic to improve security and performance. So each VLAN is acting as its own little LAN, and then if somebody breaks into that virtual LAN, it's separate from all of the other LANs. Therefore, if anything happens, it stays within that little segment, so it improves security. And of course, they're getting their own segment, so the performance for them is going to also be increased, as if they are getting their own LAN instead of sharing the data with everybody else. Now, it reduces broadcast domains by isolating traffic. So it actually, again, isolates traffic, it segments it, and then therefore you don't need to have a multiple series of broadcast domains, because you're essentially isolating all of the traffic, and then you can communicate with each one of those domains as if each one of those domains could technically share the same broadcast domain, or each one of the VLANs, the virtual LANs, the virtual logical groupings, right? Each one of those little segments could actually share the same broadcast domain that goes out into the internet, and is configured using switches, as we already just saw. The types of VLANs that we have would be the default VLAN, which all ports belong to this VLAN by default, which is VLAN 1 in most switches. And then you have the data VLAN that's used for regular network traffic. You have the voice VLAN that prioritizes for voice over IP. So this is for phone services, for actual telephones, hard lines that are coming for better call quality. And then we have the management VLAN that's dedicated for managing the switch or the network devices. And then you have the native VLAN that carries untagged traffic in a trunking environment. And so the default is where all the ports literally belong to this, because it is basically the default port on the switch, the main port on the switch. The data VLAN is for network traffic. And then you have the voice VLAN for phones, the management VLAN for managing the actual switch itself. So it's literally specific to this switch or whatever that network device would be. And then you have the native VLAN that carries the untagged traffic in a trunking environment. I also just want to share trunking in a little bit more depth with you, because you will be hearing about trunking more frequently as you go into networking. A trunking environment, and then there's also the trunking protocol. Trunking environment refers to a network configuration where multiple data streams or connections are aggregated and carried over a single physical link, essentially allowing many users or devices to share a single communication channel, similar to how a tree trunk distributes water to its branches. This is commonly used in telecommunications and computer networking to optimize bandwidth and improve efficiency by consolidating traffic from various sources onto one connection. So multiple users or devices can access the network simultaneously by sharing the same trunk instead of requiring individual dedicated connections. And this is where VLANs come in. So trunking is often associated with VLANs, where a single physical link can carry traffic from multiple virtual networks, allowing for logical separation within the network. And another concept would be the link aggregation, which is combining multiple physical connections into a single logical link to increase bandwidth, and to increase redundancy. So if we were to look at this again, right? So this would be the physical link technically, and then each one of these VLANs could be a part of that trunking protocol, where each one of these logical segmentations are using the same trunk. They're using the same physical resources to generate their traffic, right? And then link aggregation is the opposite version of this, where you have multiple switches that are combined to aggregate all of those links to create one logical link. And then when you have multiple switches or multiple routers, obviously you're getting resources from multiple physical devices, so it increases the ability, right? Increases the bandwidth. And then of course, if there's multiple routers feeding in, if one of them crashes, the network is still up. So it provides for redundancy as well. And just a couple of real world cases. We have segmenting the HR and IT departments for security. This is why we would use VLANs. And then prioritizing VoIP traffic with a dedicated voice VLAN so that you can get voice services or phone services over internet access. So link aggregation, we already touched on it a little bit. This is essentially the opposite of virtual LAN. So where you use one physical device on a virtual LAN to create multiple logical segments. With link aggregation, we are combining multiple physical devices, physical links, into a single logical link to increase the bandwidth and to provide for redundancy. So this uses link aggregation control protocol, LACP, which is part of the 802.3. So if you remember, 802.3 has to do with wired technology, and 802.11 had to do with wireless. So 802.3 AD has to do with the link aggregation protocol, and it balances traffic across all links in the aggregation group and provides failover if one of those links fails, which is where the concept of redundancy comes in. So the benefits would be to increase throughput by combining bandwidth, because again, you're creating a single logical link from multiple physical devices. So imagine multiple physical routers bringing in service, and then now you're combining the power of those physical routers into one big switch, and then now from that you're increasing your bandwidth because you're combining the power of all of those routers. And it improves redundancy for critical links in case, again, if one of those routers fails, at least you have the other routers as a backup, so it won't be as fast, the bandwidth won't be as great, but at the very least you still have connectivity. Now the real world use case would be aggregating links between switches in a data center, or ensuring high availability for server connections, and this is all because you are again combining physical devices to create one singular logical link. In case any of those physical devices fails, you have all of the other devices acting as backups or as redundancies. Now, the concept of the redundancy is actually very interesting when we're talking about networking and traffic flow, because sometimes if you have multiple switches that are acting at the same time, the traffic packet could go from one to the other without actually leaving the network. And this is considered a loop, right? So it doesn't actually leave your network, it just goes from one to another one and it goes to the next one. And so this is where the spanning tree protocol actually comes in, the STP. And it prevents loops in a network by blocking the redundant paths until they're actually needed. So if one of the switches crashes and then now you need the other backup switch, that's when it is unblocked, right? That's when the traffic for that is actually allowed, because it's no longer redundant, it's actually needed. And this is where the spanning tree protocol really excels, and this is where it shines. It prevents the loops from taking place by blocking the path for any of those redundant servers, or the redundant switches, so that until they are needed, they're essentially not functioning, right? They're providing increasing throughput by increasing the bandwidth, but you don't want the traffic to just loop between each one of them and it never actually leaves the network, or it loops through all of them before leaving the network. You don't want that to take place either. You just want the data packet to just go through the freaking switch, or I guess it would be a frame at that point. So at that point, it's a frame. It goes through the switch, and then from the switch, it gets to the router, and then it becomes a packet. So you don't want that data frame to loop between all of the switches before it reaches the router. You just want it to go through the switch and then go through the router and then leave the network and then go to the internet, right? So this is where the spanning tree protocol really shines. This is part of the 802.1 standard. So this is the first time that we're actually talking about the 802 standard. So 802.1 standard is a part, or this is where the spanning tree protocol connects to that. It identifies and disables redundant paths while keeping a backup path for failover. So these are the key features of the STP, the spanning tree protocol. Identifies and disables redundant paths while keeping a backup path for failover. And then of course, it's part of the 802.1D standard of IEEE. Now the key STP states would be blocking. So the port does not forward traffic, but it listens for the BPDU packets. And then it listens, so in listening state, it's listening for BPDU packets to determine the topology. Then in learning state, it begins populating the MAC address table, but it does not forward any of those frames. And then we have the forwarding state, where it actually forwards traffic as an active part of the topology. And then we have the disabled state, that the port is administratively shut down and it's disabled. So blocking, listening, learning, forwarding, and disabled. Blocking, it does not forward traffic, but it listens for the packets. Listening, it's actually listening for those packets to determine the topology. And then learning, it begins populating the MAC addresses, but it doesn't forward anything. And then forwarding forwards the traffic as an active part of the topology. Disabled is disabled. We have a couple of variants of this. So we have the rapid version of spanning tree protocol, and it's faster, obviously. So rapid, faster, and faster convergence than traditional spanning tree protocol. And then you have MSTP, which is the multiple spanning tree protocol that allows multiple spanning tree instances for scalability. And then the real world uses would be to avoid broadcast storms in networks with redundant links. And this is where that comes in. And then ensuring backup paths are available during link failures. And that is literally the entire purpose of this thing. So it blocks off those redundant routers, or the redundant switches, excuse me. It blocks them off until they're actually needed. And then if they are needed, then it will activate them and allow them to forward that traffic. Okay, so this is a very basic flow. This is a very basic switch interface configuration flow that we see right here. So the first command would be the interface, and then you actually choose the name of the interface. So you say interface fast Ethernet 0/1, and now you're working on this particular interface. And then you use switch port, and then you change the mode to access. So you're switching the port to access mode, and access ports are used for end devices like PCs and printers, and they're assigned to a single VLAN. So the mode is now being turned into access, and then the access is going to be assigned to this specific VLAN. So we use the interface command to actually choose the interface that we want to use, and then switch port mode to access, and then switch port using the access mode to access the VLAN number 10. This is an example workflow for creating trunking ports. And so this is used to carry traffic for multiple VLANs between the switches, and it tags the traffic using the 802.1 protocol, and so 802.1Q protocol. So again, interface, and then we're choosing the interface that we want to use or work with, and then we're going to switch the port into trunk mode. And then from there, you say switch port trunk allowed, and then you choose the VLANs, because now you're combining multiple VLANs, right? So you choose the VLANs that you would want to combine, and then they're comma separated. So in this case, VLANs 10 and 20 are going to be allowed to actually process trunking, and it's going to be for this specific interface on the switch. So if you want to set a rule for any given port to have a limitation on the number of MAC addresses that can actually access that port, we would use switch port and then go to port security. And then from there, we would say port security maximum 2. So you want to have a maximum of 2 MAC addresses that can use the given port. And then from there, if that rule has been violated, you want to shut down the port. So switch port security maximum would be 2 MAC addresses, and then for port security violation, you would shut down the port. You can aggregate the links through the command line as well. So in this particular case, instead of just saying interface and then choosing the interface, you can say range, right? So we can say interface of this range, where is the gigabit Ethernet, and then we're going to 122 technically. So it's basically just 2 of them. And then now you say that you want to channel this group, and it's going to be group 1, and then you're going to turn it into active mode. So you're channeling the group into group 1, and group 1 is going to consist of these 2 interfaces, or this range of interfaces. It could be more than 2, obviously. And then we're going to create the group, and then the mode itself is going to be active. So now this link has been aggregated, right? These 2 interfaces have been linked, and now they're active, and they're inside of this specific group for an ether channel, right? So we have now aggregated those groups, and we are combining these 2 specific. And remember, so link aggregation is when you have the physical devices being logically combined. So this is what we're doing to take these 2 physical interfaces, and we're logically combining them into this one group, and then we're activating them. So these are a couple of scenarios that could happen in the real world. We have the segmentation of the VLAN, right? So the problem would be that a company wants to isolate traffic between its various departments. So we would configure VLANs on the switch to separate traffic logically. And then scenario 2 would be that there's link aggregation for increased bandwidth. So basically the opposite of this, right? So there's a high traffic server that needs additional bandwidth. So we would use the link aggregation protocol to be able to combine multiple links into a single logical connection. And then the scenario 3 would be preventing network loops with the STP. So redundant links, this is the problem. The redundant links in the network cause a broadcast storm. So we would enable the STP so that you can spanning tree protocol, so we can block the redundant paths until they're actually needed. And then securing switching ports, or securing switch ports, excuse me. So the problem would be that there are untrusted devices that are connecting to open switch ports. So we would use port security to restrict MAC addresses on each port, or maybe even deactivate the MAC addresses, or deactivate the ports entirely, so that those ports are not accessible, and then only the ports that should be active are active. Then from there, only specific MAC addresses are available or allowed to access those ports. And that brings us to our practice questions for switching technologies. So what is the primary purpose of a VLAN, of a virtual LAN, where we segment there's logical segments inside of a network that's done from a physical device? So increase the physical bandwidth of a network. That would be a logical aggregation, right? A link aggregation. Prevent network loops in a redundant path. That would be spanning tree protocol. Segment a network into logical groups to improve security and performance. That's it. That would be the answer. I don't even need to read the other one. Which protocol is used for link aggregation? Completely spaced on this. I have not memorized these links. I'm going to say 8021Q is what I'm going to say. Or 802.380. 802.380. Very good. Okay, very good. That is indeed the answer. What VLAN type is used to prioritize VoIP traffic, right? So native VLAN management, VLAN default, or the voice VLAN. I wonder which one it is. It's the voice VLAN. Which spanning tree protocol state allows a port to populate the MAC address table, but not forward the frames, right? So you want to populate the MAC address table, so it's learning, right? So it's not blocking, obviously, it's not listening. I mean, it is technically listening, but it's also learning. And it's not forwarding anything, because it says it's not going to forward any frames. So it is learning. What does a trunk port on a switch do? It connects end devices to the switch. It carries traffic for multiple VLANs between the switches. It prevents network loops in a redundant network. Limits the number of MAC addresses on a port. I'm going to say it's going to carry multiple VLANs because it's coming from it's combining into a trunk, I believe. I think that's it. It's either A or B. I think it's B. Yeah, it is B. Carries traffic for multiple VLANs between the switches, very similar to how a trunk feeds its multiple branches. Which of the following allows multiple physical links to be combined into a single logical link, and that would be the aggregation of the links. Spanning tree protocol has to do with the redundancies and managing those redundant physical devices. VLAN tagging has to do with creating the logical separations, the virtual LANs. Port mirroring literally has nothing to do with any of this conversation. It basically mirrors the traffic that is given on any given port. So link aggregation is when multiple physical links are combined into a single one. What is the purpose of the 802.1 Q protocol? To prioritize traffic in a VLAN, to provide redundancy network gateways, to tag VLAN traffic in a trunking environment, to secure ports on a switch. Oh man, I would be completely guessing on this one. Oh, okay, so to tag VLANs, VLAN traffic in a trunking environment. 802.1Q is to tag VLAN traffic in a trunking environment. Okay, so these things, if they're showing up as practice questions, then it's very, very important to know these freaking standards. And I obviously, they are important to know. I'm not even going to pretend like they're not important, and this all falls under memorization. Unfortunately, like there are certain things inside of networking education that really does fall under memorization. Now, I will tell you this, that when you actually go into the real world, you can Google a lot of these things, and you'll have access to spreadsheets and documents and things like that you can search through. But it is really good to, at the very least, learn them well enough so that when you go into the examination, assuming that you want to take the examination, you will be able to recognize these various standards. Which variant of the STP offers faster convergence time? So the spanning tree protocol, and if it's faster, it means it's rapid, right? So it's the rapid spanning tree protocol. Which feature on a switch restricts the number of MAC addresses that can be learned on a port, right? So it would be port security that restricts the number of MAC addresses that can be learned on a port. VLAN tagging is tagging which VLAN belongs to what department, basically. And trunking is combining the various VLANs. And then the Ether channel I think the Ether channel is also connected to, no, Ether channel is for the link aggregation. So it would be port security. That would be my guess. Very good. Company experiences a broadcast storm due to redundant links. What technology can resolve this issue? So you have a broadcast storm and there are redundant links. So it would be the spanning tree protocol that has to do with that specific problem. So redundant links and a broadcast storm. And that's it. And that is officially it for switching technologies. And now we can start talking about everybody's favorite thing. What's the Wi-Fi, right? So wireless networks. To get access to the Network Plus notes, as well as the mock exams and the practice question slides, join the Hackaholics Anonymous community. If you join as a cyber agent, cyber guardian, or cyber master, you'll get access to all of the notes, the mock exams, and practice question slides, as well as many other perks that are available to Hackaholics Anonymous members, like Python automations and exclusive content, as well as monthly live streams with me. And to join, you can click the link in the description below, or you can go to our homepage and click the join button there, or you can simply go to youtube.com/@HankHacksHackers/join, and you'll be able to join Hackaholics Anonymous. Now let's get back to the Network Plus training. And now it's time to talk about everybody's favorite subject, which is Wi-Fi. So wireless networks. And wireless networks enable devices to connect without physical cables. Wi-Fi. Everybody that is watching this should be brutally familiar with Wi-Fi. You should know exactly what it is. You may not know the encryption standards, or you may not know, some of the other technical aspects of it, but I know for a fact that that there's such a thing that exists that is called Wi-Fi, and then you're probably watching this video connected to a device or using a device that is connected via Wi-Fi. I'm willing to bet that 99% of the people that are watching this video are on Wi-Fi versus being on a wired network. So this is the brilliance of the modern era, where for the most part, every device can connect to Wi-Fi and you can get pretty much anything done. The one thing that I think is the one activity that really does require something like a wired connection would be if you really are brutally dependent on the consistency of the connection, the integrity of the connection, how persistent the actual connection is without any gaps in the coverage or the speed or anything like that. And the only thing that I can think of, because I'm a super nerd, is video gaming. And there are people who have hardwired Ethernet cables to their PC towers that gives them a very, very powerful access. And I mean, based on just some of the data that we've covered so far, we know that wired connections can actually be significantly faster than Wi-Fi connections. So there's that part of it where, you know, if your game loads faster, especially if you're doing like a multiplayer network connected type of a game like Call of Duty or something, where you would have to play against other characters, and a delay in the game data being served to your computer could actually mean that you could lose the game. And if somebody has a faster connection and it's a more persistent connection because it's a wired connection, then they have an advantage. So that's one of the big things that I think of when I think about like the power of wired connection versus wireless connection. But for the most part, you can pretty much do anything that you would do with a wired connection using a strong wireless connection. So just to kind of give you the visual of what this actually looks like, this is a very basic Wi-Fi network that has been set up, right? So in this particular case, we have the internet, the World Wide Web. It's being fed into the router. The router connects to the switch, and then the switch connects to the Wi-Fi access point. And then the Wi-Fi access point provides the Wi-Fi signal for mobile devices or laptops, which are still technically considered mobile devices, for those devices to be able to connect to the internet, right? And in most modern homes, so this technically would be a business type of a setup. In most modern homes, the router and the switch and the Wi-Fi access point are all in one device. So for example, in our home, our basic internet that connects all of the TVs and everything like that is actually being fed from one device that serves as the wireless access point as well as the router, and technically the switch as well, because you could actually hardwire devices to it through the ports that it has in the back of the device. So that's the overview of wireless networks. Frequency bands are the main measuring stick or signal gauge that we can think about when we're talking about the strength of a Wi-Fi connection, as well as how far we can be from the router, how wide of a range we can have from the router to still be able to get a connection. So the lowest in this series would be the 2.4 gigahertz, which is, it's the widest area of coverage, meaning you can be the furthest from the router and you'll still be able to get a connection. Now, that being said, it's not going to have the fastest speed, obviously. This is also really good, or it's at least better compared to the other ones, for penetrating through walls and obstacles. But it's prone to interference because there's only 3 channels in most of the regions that are available for this, meaning number one, you can actually intersect with other networks, but there's also the concept of you have microwave devices or, you know, smart appliance devices that are inside of a home that will require connection to this specific band. And then you also have things like either cordless phones or IoT devices, anything essentially that would count as a smart appliance. And an IoT device could technically be your TV. It could be your garage door opener. It could be the microwave. It could be the refrigerator. It could be literally any smart appliance that you have that will connect to the internet that doesn't need crazy signal for video streaming or video gaming or any of these types of things. So because of the fact that there are more devices that are connected to it, and it has a limited number of non-overlapping channels, which is 3 in most regions. So imagine there are 3 non-overlapping channels in most regions, which means that there is actually a possibility that you can have your connection intersect with other people's routers and networks. So that's a big disadvantage. Then we have the use cases for this. So it could be, again, internet browsing, like general internet browsing, low bandwidth applications that don't require a strong signal because they're not doing any heavy lifting. So these could be smart appliances or IoT devices. This is the very basic type of wireless band that's available, and every single Wi-Fi router will at the very least provide you with a 2.4 gigahertz band. If it doesn't offer you anything lower, or if it offers you something lower than this, that means that you're in like the primeval ages, like you have a very old device and an old internet connection, or you're in a really remote location. But even with that, things like I believe it's Starlink, the connection service, that the Wi-Fi connection, internet connection service that Elon Musk has started, that allows you to, but they have, I don't know, probably something like 1,000 satellites, probably more, that are orbiting the planet right now, and you can get Wi-Fi service with a small box, and you can take that to the most remote locations of the world, and at the very least you'll be able to get a decent, strong connection. I think it's definitely stronger than 2.4 gigahertz. So that's a little bit of independent study for you to see what is available. But at the very least, in this day and age, in 2025, 2.4 gigahertz would be the bare minimum that you would get as far as a signal or a connectivity band, a frequency band. And then we have the real players, which is the 5 gigahertz and the 6 gigahertz bands. And the 5 gigahertz is, I think, the most common. So it has really high speeds compared to 2. Obviously, it's pretty much at least 2x of what's available on a 2.4 gigahertz band. And there's more non-overlapping channels that are available. And there's less interference compared to 2.4 gigahertz because, for the most part, all of your smart appliances and devices will be connecting to the 2.4 gigahertz band, and all of your important devices will actually be connecting to the 5 gigahertz. Now, the disadvantage of this is that the range of it is shorter, so you actually have to be closer to the router for this to effectively work, and it's less effective at penetrating things like walls, right? So you do have, most likely you probably have to be at the very least inside the same building, I would say, but maybe within, like, you could be a room over from the router, maybe 2 rooms over from the router, but the signal won't be that great at penetrating through walls. Again, but it also depends on the type of router that you have, the strength of the connection itself. There are other variables that feed into this, but we're talking about generally, it's definitely a shorter range than what's available on 2.4 gigahertz, and then it's less effective at penetrating through walls. And this is what you would use for streaming and gaming and any kind of a high bandwidth application, or an application that requires a strong connection, a fast connection. And then 6G is, or 6 gigahertz, I should say. This is the Wi-Fi 6E. So this actually requires a router that actually supports this 6 gigahertz frequency band. And if it does, then this is additional bandwidth, reduced congestion, because there aren't very many devices that even support this. And it has much higher speeds, obviously, and more simultaneous connections. So this is the cream of the crop as it stands right now. But it requires devices that are actually compatible with Wi-Fi 6E, including your router, as well as your actual devices like your computer or your phone that would actually be compatible with it. And this would be the shortest range from the router. So this would be you have to be the closest, as far as the comparison between these 3 different frequency bands is concerned, you would have to be closest to the router for the 6G to work, as well, or 6 gigahertz. I keep comparing, because 6G technically would be for your mobile device, like your cell phone device, and that's not the proper terminology for it. So for the 6 gigahertz band, you would have to be closest to the router, let's say in the same room, or at least, let's say, a room over, again, depending on the type of equipment that you're using, the type of router that you have. And this is the best for a high density environment, like a stadium or an office that has a lot of employees, because there are a lot of devices that connect to this specific band, or they want to connect to Wi-Fi. And if you have a lot of devices, let's say hundreds, if not thousands of devices, sorry about that. If you have hundreds, if not thousands of devices, then your signal needs to be extremely strong to be able to support that congested type of an environment. Now, the SSID, the Service Set Identifier, is basically the name of the Wi-Fi network. So usually there's a default one that's assigned, so AT&T, and then just a bunch of letters afterwards, or Spectrum, bunch of letters afterwards, something like that. And this is the name that enables the device to be able to find the network, to identify the network, and then to be able to connect to it. And the concept of SSID broadcasting is what allows the devices to be able to detect the network. And then you can disable the SSID broadcasting to obscure the network, but this doesn't fully hide it. This is not a security feature that prevents other stronger adapters, for example, like a Wi-Fi adapter, or using a tool that supports a given Wi-Fi adapter, and then using something like Aircrack NG, which is a penetration testing tool that is used specifically for hacking into Wi-Fi networks and Wi-Fi connections. So it doesn't necessarily mean that somebody won't be able to use those tools to find your network and to be able to connect to your network. So you should have a really strong password. It should not be the basic default passwords, although the carriers, the internet service providers, are actually getting much better at issuing complex Wi-Fi passwords as their default passwords, as like their entry when you first get connection. But they are passwords that are really hard to remember, which is still fine, because if somebody's actually trying to connect to your network, you will most likely, at least I get this on my Apple devices, where I'll get a pop-up on my MacBook or on my iPhone where it says, so-and-so is trying to connect to your Wi-Fi. Do you want to share your password? So you can actually share the password with them without them knowing what the password is, and then without them having to type it up, because it's like a random series of characters and numbers. So it makes it a little bit more convenient to do, and it's also it's somewhat of a security feature, because if somebody that you don't recognize is trying to connect to your Wi-Fi network, then it's like, okay, well, no, I don't want to share my password with you. And they won't be able to guess it, because it's a very complex password. So I would say the length of the password is pretty good if you need to have, because I think they give you a 12-character or 14-character password, and it's still random letters and numbers. So it is technically secure compared to the word password, for example, or just some like random, really basic word. So that's better than that. But if you can actually increase it to a 20-digit password or a 32-digit password, something like that, and still keep it super complicated, then that would be most likely the best scenario for the security of the device. And then just make sure that the device is obviously physically secure, that nobody that shouldn't have access to it can't get access to it. And that, as far as home internet connections are concerned and home networks are concerned, that's really the best that you can do. But there are, of course, you can get modems and routers or Wi-Fi access points that have internal firewalls. AT&T actually has a firewall that is a part of the service that just comes when you get your internet service through them. And there's a variety of different security appliances or security software that you can use to ensure that your Wi-Fi network is secure. Now, the naming practices specifically, so going back to the SSID, going back to the name, your service set identifier, excuse me, I'm just all over the place, your service set identifier, the naming would be to use a unique name that's descriptive to different networks if you have multiple networks inside of a building that you're managing for a business. So the network that would be dedicated to the IT floor, for example, or the network that we dedicated to the marketing floor, so on and so forth, that could be a unique name that you have for it. And then you could have the acronym for your business. So let's just stick with AT&T. So let's say your business is actually AT&T. That's the company that you work at. So you'd be like AT&T_marketing. And that would be like the name of the Wi-Fi network for the marketing team. something like that. So avoid including personal or sensitive information in the SSID. I feel like that would be a given. That's like common sense, but some people do it. They put their name in there, or they put their family's last name in there, something like that. That would be very silly. Don't do that. Keep it random. Keep it unique. To keep it separate. And then if you have multiple wireless access points, assign the descriptive names to them so that you know which one belongs to what or belongs to what department. And then some wireless access points support multiple names, and each is designed for different virtual LANs for network segmentation. And we talked about virtual LANs being something that is a service that's available through the switch. So you can actually get a wireless access point that allows multiple SSIDs because it kind of technically is acting as a switch. Therefore, you can have one SSID that is for one network segment that would be for the marketing team, and another one would be for the IT team, so on and so forth. In the school where I was at, where we were studying cybersecurity, when I first started out in my studies, we had 2 classrooms, and the 2 classrooms had 2 Wi-Fi networks, and it was all set up through the same physical devices. So there were switches that were available, or there was a switch that was available that would break out to the 2 different classrooms, and then from there we would have the physical wired connections that would go to the actual towers, the PCs, and then there were the Wi-Fi networks that were available as well. And all of this was done through one room with one set of physical devices, the physical network devices. So this is it for the SSID concept. A real world example of what SSIDs are actually used for and how they're used, and this is very common, and I'm sure you've ran across something like this before. This is where you go to a business and you want to connect to their internet, and they have something for the employees of the business, their internal network, and then they have something for people who are just guests that are visiting the building and they just need access to Wi-Fi. And the guest SSID is assigned to a VLAN that restricts access to the internal sources, so their intranet and their internal devices and the various segments of their network that should only be available for employees. So this is a very, very common scenario. I've ran across this dozens of times. I'm pretty sure you probably ran across this as well, where there's the internal network, the internal Wi-Fi, and then there's the guest network. And usually the guest network is also on a lower frequency band as well, because they want to reserve their highest speeds for their employees. Which brings us to encryption. So encryption is actually obviously a very, very important concept in Wi-Fi or in networking or cybersecurity or in IT. It's a really, really, really big concept, and it's very important. And as we've already talked about it in multiple instances, there's various types of encryption. And of course, there's various types of encryption for Wi-Fi. So WPA2, which is the Wi-Fi Protected Access version 2, and then there's the Wi-Fi Protected Access version 3. And these are, obviously, version 2 was the predecessor. It was the first one that came out, and then version 3 came out shortly after. And so version 2 uses the Advanced Encryption Standard, AES, for strong encryption. There's the personal mode, which is WPA2 PSK, and we can just say WPA2 P would be the personal, and then we have the enterprise mode that actually has the word enterprise, and it's a little bit easier to remember. Or if you see that it's not enterprise, you can pretty much say, okay, this is the personal mode. The personal mode secures networks with a shared password. The enterprise mode uses a radius server for authentication. Radius stands for the Remote Authentication Dial-In User Service. So remote authentication dial-in user service. And this is a networking protocol that authenticates and authorizes what's happening and authenticates and authorizes users who access a network remotely. It's a key tool for cybersecurity because it helps prevent unauthorized access to networks. So obviously this would be something for a business environment, right? You want people to not be able to access a very sensitive part of your network. So how this works is the server validates user security information, then the client or the network access server communicates with the Radius server, and then the Radius server performs authentication, authorization, and accounting, and then the Radius provides a centralized authentication mechanism. So the server, the Radius server, validates the user security information. The Radius client, or the network access server, communicates with the Radius server. So your computer could actually be a client, or it could be the network access server that's communicating with the server, with the Radius server. The word server is losing its meaning. The Radius server performs authentication, authorization, and accounting. And accounting is not a financial term. It's to account for the activities of the people or the devices that are connecting to this specific network. So it keeps you accountable, right? It keeps you responsible. It makes sure that people don't do what they're not supposed to do. That's what accounting is. So then the Radius server provides a centralized authentication mechanism. So that's what Radius is. I just wanted you to know what it is because it is a very important concept as we talk about networking, and this also becomes an important concept when you go into studying for cybersecurity. Should you ever actually be interested in studying for cybersecurity, the remote authentication and dialing user service is a concept that you should be familiar with. The advantages of the Wi-Fi protected access 2, the advantages of WPA2, is that it's stronger security compared to older protocols like WEP or the first version of WPA. The limitation is that it's vulnerable to brute force and dictionary attacks if weak passwords are used. So again, going back to this concept of using strong passwords or changing the default passwords and using long form passwords, so don't limit it to 14 characters. Most of the Wi-Fi routers and internet service providers literally allow you to set like a 40 character password if you wanted to. So do that. If you can, do that. Set up a long I like using sentences and long phrases, and those things are amazing. Like, they're very, very useful because you can actually remember them, because you just have to remember this phrase, and then what happens is that it becomes a long password. And then especially if you capitalize, for example, the first letter of every word in the phrase, that would be one thing. You can capitalize the last letter as well, so the first letter and the last letter. You can turn all of your S's into $signs. You can turn all of your E's into the number 3. There are so many different ways to make sure that you increase the security of it. You can turn all of your A's into the @ symbol, and it just goes on and on and on. So if you have a long password, so let's say this is the password, secures networks with a shared password. Let's say that's the actual password. You remove all of the spaces, obviously. You capitalize all the first letters. You replace all of the E's with 3s, and you place all of the S's with $signs. So the first S on this, I would keep that as an actual S. The last S on the word secures, I would turn that into a $sign. I would turn the S in networks into a $sign. I would keep this S for shared as a capital S, and then the 2 S's over here would be turned into $signs. The letter O could be turned into a 0. There are so many different ways to do this. But again, if it's just a long password and you've done all of the using the various capital letters, lowercase letters, special characters like @ symbols and hashtags or whatever, as well as numbers, then you're pretty solid. And there is no dictionary that is going to have this be stored in it as one of the passwords. It's just not going to happen. So if you, and then it's also really fun to create words in your own language. So essentially use a phrase from your language, but then use English lettering to, verbalize that phrase or to speak out that phrase. That would be guaranteed non-existent in any kind of dictionary password. So, or password dictionary, excuse me, dyslexia. So yeah, there's so many different ways to create passwords that for sure are going to be secure, and they're not going to be inside any kind of a password dictionary, and you can remember them. So it won't be just a random series of 15 characters, and then you can actually create a password that's 40 characters long. And I mean, you're so solid. After that, nobody's going to try to hack you, because I mean, until quantum computing becomes a thing that everybody's walking around with a quantum computer in their pocket, until that becomes a thing, you're pretty freaking solid, which I foresee as being quite a time away from now, because the physical infrastructure for quantum computing to be inside of people's pockets that is not even close to existing. You need extremely powerful computer chips, and it's just that, yeah, I feel like that's still quite a time away. We do have quantum computers that are becoming common, and Google has like a really strong one, and I totally understand that they exist, but for it to be accessible to any random hacker, I think it's quite a time away. So they still have to get past, encryption, and if you have a strong password, then the encryption is just going to be very, very impossible to break unless they have that password. So that is it for WPA2. WPA3 is the next level. So it's the one that came after WPA2, very similar to how version 2 came after the very first version. So WPA3 replaces the version 2 and introduces more robust security features. One of them is the SAE, which is the simultaneous authentication of equals. Now, this provides secure password-based authentication that is resistant to brute force attacks, meaning brute force attacks is basically when somebody just tries a password or different passwords just over and over and over and over and over and over again, and they don't get locked out, right? This service itself doesn't get locked out. We call that rate limiting. So rate limiting is something that is usually used when you're managing users and you want to lock out a user if they do 3 incorrect password attempts. That's usually used inside of that context. In the context of WPA3, we talk about it as the SAE, which is the simultaneous authentication of equals. And this is what provides the resistance to brute force attacks, essentially by making sure that either the system locks out, or for a certain amount of time nobody is allowed to use passwords anymore, or the network itself will stop all connections and it'll send a notification to the administrator user, which is the person that is the main account holder for the internet service. So there's a few different ways that it could actually work, but the point is that it provides resistance to brute force attacks. And then there's the forwarding of secrecy that ensures that intercepted traffic cannot be decrypted even if the password is compromised later. So this is very interesting. So forward secrecy ensures that intercepted traffic, so if somebody's sitting there sniffing your traffic, it cannot be decrypted even if the password is compromised later. So if they have your password, they still aren't able to decrypt the traffic that they've captured, which is very useful. So the key to decrypt that traffic is not the password of the Wi-Fi. Does that make sense? So usually, or not usually, pretty much 100% of the time, to be able to decrypt something that's been encrypted, you need the key. And the key could be a password, it could be some kind of a ticket, like a token or a ticket, something like that that's been generated, or a certificate, something like that that's been generated that is used to decrypt that decrypt that encrypted data. I thought my dyslexia kicked in again, but that time I actually had it right. So there's a key that you need to decrypt something. And in the case of Wi-Fi, the password could be the key, but in this case, it's not, because the password is just going to grant someone access to the Wi-Fi service so that they can get on the internet, but they can't use that password to decrypt the intercepted data, which is very, very important. So the advantages of WPA3 is that improved protection against offline password attacks, which is basically what we're talking about, and that's what a tool like AirCrackNG kind of does, is that because they're not connected to your network, their device is technically still offline, but they're using this tool along with a network adapter that can connect to their computer that supports AirCrackNG, which is Discover mode. So as long as that is available, then they can go ahead and run AirCrackNG offline without being connected to the internet and still try to get into your system. So this actually has improved protection against those types of attacks. And then we have the more secure open networks with opportunistic wireless encryption. opportunistic wireless. I feel like that's how you're supposed to pronounce it. I don't know if my accent is like kicking in, but opportunistic. Okay, whatever. It's more secure open networks with the opportunistic wireless encryption, also known as O. The limitations is that it requires newer hardware and software compatibility. So this is for more recent devices. However, granted, this version of Network Plus is not the absolute most recent as of 2025. So this, I feel like most devices, if you've gotten them over the last year or two, most devices support WPA3, and then same thing goes for your internet router and your wireless access points. If you've gotten it over the last year or two, it should support WPA3. Now, if you've had your router for many years, then I would highly recommend you contact your internet service provider and you say, I want an updated router because I want to make sure that I'm on WPA3, or just call them and be like, is my router using WPA3, Wi-Fi protected access level 3, version 3. So if we did a side-by-side comparison of these guys, encryption level for WPA2 is the advanced encryption standard. On WPA3 is the advanced encryption standard with the authentication of equals, so the secure authentication of equals. The authentication mechanism would be the PSK, which was the one that stands for the personal version of the WPA2, and then as well as the, of course, remote authentication of user system, dial-in, remote authentication of dial-in users. And then we have on WPA3, we have the secure authentication of equals as well as radius. And then protection against password attacks is limited on WPA2, but there's a stronger resistance on WPA3. And then open network security, there's none that's available for the WPA2, but on WPA3, there's the opportunistic encryption for open networks, meaning networks that don't have Wi-Fi passwords connected to them. So just as a general gist, obviously we can say, okay, WPA3 is the more secure version of this, and we should be using WPA3, and WPA2 is more secure than WPA, like the very first one that came around. And that's, it's better than having WPA just by itself. So these are the takeaways from this. Now, the details are stuff that you would have to study and kind of wrap your head around to just make sure that you understand why WPA3 is more secure than WPA2. But for the most part, we can conclude that WPA3 is more secure. Now, the questions that you'll probably run across would that be like, yeah, this so-and-so network is using WPA3 and they want to make sure that they have protection against password attacks. So what kind of protection does it provide against password attacks, or what kind of authentication mechanisms are allowed through WPA3 that will protect against these types of things? So you will most likely get a question where they just throw it in there that this system, this company is using this type of encryption for their Wi-Fi, and this is their scenario, this is their problem. And then, you would say the network administrator needs to do X, Y, and Z to make sure that it's done. And then you have to choose the actual right choices based on the version of the encryption. So you would act as the network administrator, and then based on what you know about WPA2 or 3, you would say, okay, yeah, they can actually do protection against brute force attacks, or they can use the secure authentication of equals to protect against brute force attacks, something like that. Now we have a time for scenarios. So scenario time is where we're at. Scenario number 1 is the optimizing frequency band selection. So here's the problem. A home network experiences slow performance due to interference. So they're probably on the 2 gigahertz, right? So the solution would be to configure the network to operate on the 5 gigahertz band for higher speeds and reduce the interference, and then leave all of their smart devices or whatever, or not their smart appliances, leave all their smart appliances on the 2 gigahertz band, because again, the 2 gigahertz band usually has a maximum of 3 channels per region, which is insane, and there's a lot of interference from a variety of other devices. So scenario number 2 would be the securing of a corporate wireless network, and the problem is that employees connect to the corporate network using a shared password. So you want to upgrade to WPA2 Enterprise, or WPA3 that has the remote authentication dial-in user system for stronger authentication, right? So make sure that their authentication is actually being protected against brute force attacks or something like that. Then we have the guest network segmentation. And the problem is that a business needs to provide internet access to guests without exposing internal resources. So this has to do with SSIDs, right? So if you remember, we had that example. So you would create a separate SSID for guests and assign it to a VLAN that has restricted access on that Wi-Fi network so that the guests that connect to your Wi-Fi can't just roam around and start doing things, and then maybe even limit the type of things that they can do. For example, running an Nmap scan, like an Nmap scan from anybody who's connected on the guest network should not be able to yield any results because everybody else, all the employees and all the sensitive devices are on a completely separate network. So if they ran something on the guest network, I would say they shouldn't even be able to run it. But if they did run it, they would only see the devices that are on the guest network. That's still a position, like potentially hazardous environment, and they could still hack your guests, which is not a good idea or not a good thing that would happen. But you could completely limit what people can do when they connect to your Wi-Fi. It's actually something that you can do, and that includes accessing resources on your network, but as well as the types of activities that they can run and what websites they can visit. You know, you don't want somebody watching porn when they're connected to your guest network, which I have actually seen people do in a lobby of a building. The guy's like, what? And I'm like, dude, what? And he's like not shy about it, and I was like, okay, this is ridiculous. Like, some people are freaking crazy. Then we have scenario number 4, which is implementing WPA3 for modern devices. And the problem is that a company wants to ensure the highest level of wireless security for new devices. So we would deploy the highest level, which is WPA3 encryption, to protect against offline attacks and secure open networks. And we have finally arrived at our practice questions. So let's go. Which frequency band is more effective at penetrating walls and obstacles? So if you remember, first of all, 10 gigahertz is not an answer that we have over here. So 5 and 6 gigahertz are not good at penetrating through walls, and you have to be closer to the router, which means that 2.4 gigahertz is the one that's really good at penetrating walls. What is the primary benefit of using 6 gigahertz introduced with Wi-Fi 6E? Better range than 2.4. That's not true, because 2.4 actually has the better range. Reduce interference with increased bandwidth. That is the answer. I would say that's my first answer. Compatibility with legacy Wi-Fi devices. That is not true, because the Wi-Fi devices actually have to support the Wi-Fi 6E. And support for broadcasting hidden SSIDs. And I don't think that was even listed as one of the benefits. So broadcasting hidden SSIDs. That I'm going to say that's not an answer. So support for broadcasting the hidden SSID, that would not be anything that Wi-Fi 6E would do. So reduce interference, increase bandwidth. There we go. What does SSID stand for? It is the Secure Set Identification. It's not the Standard Service Identifier, the Service Set Identifier, Secure Service Identification. Oh, actually, you know what? It's not secure. I think it's probably Service Set Identifier. I think that's what it is. Service Set Identifier. Yeah, okay, cool. Immediately I was like, no, secure, yes. Because I do remember the word set, and I do remember some kind of identifier identification, but it is identifier. So it's not identification, it is an identifier is what the SSID is. And then we have the service set identifier. Which encryption standard uses simultaneous authentication of equals, the SAE, for secure password-based authentication? WEP is not the one, and WPA is definitely not the one, because these are the older versions, the less secure versions. So we have either 2 or 3. Now, I mean, based on what we just reviewed, I know that 2 does not offer the SAE. So it would be WPA3. What is the main purpose of a VLAN assignment to an SSID? To prioritize voice traffic? That's not true. To segment the network traffic for security and management? That would be a good one. To allow hidden SSIDs to be broadcast? That is not the case. to assign static IP addresses to devices automatically. That is also not the case. Assigning static IP addresses to devices automatically is an oxymoron kind of a phrase, because automatically assigning IP addresses is not a static. Okay, whatever. Moving on. I would say it's B. Very good. All right, which encryption standard is more resistant to offline password attacks? So it's more resistant to offline password attacks. And again, EP and PA, these are the older ones. So this would be the one that's more resistant to offline password attacks, which is WPA3. What is the purpose of disabling the SSID broadcasting? And it's to be more obscure, right? So that people can't just find you. But again, it's not a security mechanism. So to increase wireless network range, nothing to do with it. To improve network security by hiding the network name, that could be it. To segment the traffic into separate VLANs, that's not what it does. To optimize traffic flow between wireless clients, that's not what it does. So we're improving the security by hiding the network name, but it does not mean that people can't find you, right? So there we go. Now, a company wants to prioritize, and by the way, I do realize that this is like, it's kind of like an oxymoron as well, where I'm like, you're hiding the network name, but it doesn't mean that people can't find you. But it's because like there are ways to get around something like this if you're a functional hacker, and somebody can technically get around it. But for the intensive purposes of Network Plus, because we're not talking about Pen Test Plus, we're not talking about ethical hacking. For the purposes of Network Plus, when you hide the network name so that somebody who's trying to connect to your network, they just go on their Wi-Fi or their network services on their laptop, and they try to find all of the local network connections, the Wi-Fi connections that they can connect to, your name, your network name won't show up, which means that they can't even see you, which means that they can't connect to you. But if somebody's actively trying to hunt down various network connections, and they use a variety of different pen testing tools, they can bypass this. So it was already mentioned to us that hiding or disabling SSID broadcasting is not necessarily a security feature, right? It's just something that we do as a strategy to improve the security. A company wants to prioritize VoIP traffic on its wireless network, which is voice over IP. What configuration should they use? So do they create a dedicated voice VLAN? Do they disable the SSID broadcasting for the voice network? Do they enable the WPA2 enterprise for all devices? Do they configure the 2.4 gigahertz band exclusively for VoIP traffic? So they want to prioritize VoIP traffic on the wireless network. What configuration should they use? I would say dedicated voice VLAN would be my answer. Disabling SSID broadcasting has nothing to do with that. Enable the WPA2 enterprise for all devices. I don't think that has anything to do with this either. And the 2.4 gigahertz band doesn't seem like a right answer. I'm going to say create a dedicated voice, and that is indeed the answer. Excellent. What feature in WPA3 secures open wireless networks by encrypting the traffic without requiring a password? So again, it's encrypting the traffic, but there's no password requirement, meaning it's an open network. So that was the O, the opportunistic wireless encryption. So simultaneous authentication of equals has to do with protection against brute force attacks. Advanced encryption standard is just an encryption standard that WPA3 actually uses. And then VLAN tagging has to do with just identifying the various virtual LANs, the virtual network segments that you have. So it's the opportunistic wireless encryption. O. Which frequency band provides the most non-overlapping channels? So overlapping channels, meaning if 2.4 gigahertz has 3 maximum channels per region, it has the least non-overlapping channels, right? So which one has the most? That would be 6. Now 10, whenever that comes around, that'll probably be the next answer. But 6 is our answer for now. And let's see. All right, so we are officially at 2.4. Let me just make sure. Yeah, so we are officially at 2.4, the physical installations. To get access to the Network Plus notes, as well as the mock exams and the practice question slides, join the Hackaholics Anonymous community. If you join as a cyber agent, cyber guardian, or cyber master, you'll get access to all of the notes, the mock exams, and practice question slides, as well as many other perks that are available to Hackaholics Anonymous members, like Python automations and exclusive content, as well as monthly live streams with me. And to join, you can click the link in the description below, or you can go to our homepage and click the join button there, or you can simply go to youtube.com/@HankHacksHackers/join, and you'll be able to join Hackaholics Anonymous. Now let's get back to the Network Plus training. So physical installations, as the name implies, this is the actual network infrastructure and the wires getting connected to the various routers and the switches and all of that stuff. And this is where literally the actual network itself was built, like the physical network is built. So you want to make sure everything is organized. You want to make sure all the things are properly connected. There's no cuts in any of the wires. The powers or the power systems are good. The power wires, the cabling, and you're using the extension cords that actually have circuit breakers in them, and that just a lot of different things that will make sure that your physical devices of your network are secure. And then if there's a lot of devices inside the room, you want to make sure you have a cooling system or some kind of a AC that's like a portable AC that's in there, something, right? So the key considerations includes the rack systems, and then the cabling management and reliable power delivery to minimize downtime and ensure scalability. And I'm just going to throw in there cooling as well, because these things can get very hot. They're running all the time. They're all sitting in the same room. For the most part, they're going to be all sitting in the same room. So there needs to be really good insulation. There needs to be a good cooling airflow that's going inside there. You don't want dust to get into this room. This room should be as clean as humanly possible, so on and so forth. So physical network setup is essentially just making sure that the network has the connection that it needs, but it's also the one element of it that you can pretty easily mess up if you are disorganized or if things overlap. And I'll show you as we go along. You'll see what I'm talking about. So this is just a little image here. And I was half expecting to see homeboy's butt crack, like the plumber's butt or whatever. But this is, I mean, I think for the most part, this is actually really good setup and design, and things are very well organized. What we see on the left side here, I think, is the stuff that they're still working with. And these are the wires that are either coming into the building from the internet service provider or leaving this room to go somewhere else, right? To actually go. And there's also the wires up here, and there's all these wires up here, and look at how they're leaving the room from this corner right here. So this is a really big physical setup that's going on for this network room. And they also have their computer here that is going to be used to configure all of these physical devices, which is amazing. And we also have another computer here. And there's a dude on the floor that's doing some wiring, and then this dude is being his moral support, right? So this is a really, really, really good room. And this is actually, I mean, this room probably supports 1,000 connections at least. This is a strong room. It seems kind of chaotic, but for the most part, I would say that's a really strong room. And then when you look at the various other potential rooms that are available, I did see like an image that was like really, really clean. Yeah, this is the image right here. This is like a really clean image of just, oh, of course we can't zoom into it. Maybe I can zoom in like this so you could see. Look at how organized these wires are. I mean, there are so many freaking wires. Like each one of these things right here probably has between 40 to 50 wires coming out of it. And then you multiply that by, I don't know how many racks these are. There's literally over 1,000 connections just in this image by itself. So this is, it gets pretty crazy. Like these setups get really, really crazy. And again, this is another one. And this one seems a little bit more chaotic than the last one that we saw. But again, look at, there are literally thousands of wires. So this is actually what you're looking at if you want to go into building server rooms and building network rooms with all of the network devices. This one's kind of cool because it actually has these lights, and the neon lights are always really cool when you when you think about a system. And then you have really like bad. This is not good. This is really, really dangerous, and obviously really hard to figure out what's going on. So it's like, this is bad network management. That's bad organization. So yeah, we just have a lot of different examples that we can use for good examples, but you also need to know that there are some really bad setups and really ugly networks. Look at this. So this all has to do with what? Physical installations of the network. So let's go into all of the different elements to make sure that your physical installation is beautiful. A rack system is the skeleton of the whole thing, right? So rack systems provide the framework to house the network and server equipment. They offer organization and accessibility and scalability. It's like a rack. So if you've ever been to any kind of a store where they have things that are on display, usually those things are sitting on some kind of a rack. So this is no different. This is essentially the skeleton. I like calling it the skeleton because it literally looks like the skeleton. So you have the open frame racks that are used for equipment that require maximum airflow and accessibility. And they're common in server rooms and data centers because the server room itself is locked, and the data center itself has security, and it's hard to get into the room that has the open frame rack. And then you have the enclosed rack that's fully enclosed with doors and side panels for added security and airflow control. And it can also be locked, right? And it's suitable for sensitive equipment in shared environments. So multiple people can get in this room, multiple people from multiple organizations and companies and things like that. So this one, you actually lock the rack itself. So this is what they look like. These are the open racks. Very simple to understand. We can try to understand. I mean, you can see why they call them open racks, right? They're racks. You can mount various things onto these the holes that are drilled into these various points, and then it even has the measuring units that are available over here, which we'll actually talk about in a little bit, because they actually come in different, it's weird, but there's different measurement units for these rack systems. So these are the open racks, and this is the enclosed rack. So you can see that it actually has a door, right? And it has all of this, the panels on the side right here are actually protected by walls. It does have holes in the front of it, and probably holes like towards the back of it that are similar to this, that will allow airflow to be a little bit better. There's a lock on the door right here and a latch, and the wires that leave this are going to just be the wire body that's going to leave it, not the port. The port itself is not going to be exposed so that, you know, somebody can plug something into it, right? So this is going to be pretty much enclosed for the most part, with the exception of the ventilation holes that are available, and then it's going to straight up just be locked, right? So this is what we call an enclosed rack. Now, this is what I was talking about when I was talking about they have their own units of measurement. So the standard height measurement for rack-mounted equipment is called the rack unit, and one rack unit is equal to 1.75 inches. So 10 rack units would be 17.5 inches. 100 rack units would be 175 inches. So this is important to kind of wrap your head around when you're talking about physical installations of network devices. The rack unit, so if somebody says that this is, you know, it's a 25 rack unit, you need to take that 25 and multiply it by 1.75 inches to actually get the inches. You can't use just a normal measuring tape to figure this out, because they're not talking about, if they say if it's 25 units, they're not saying it's 25 inches. So you need to take the 25 units, multiply by 1.75 inches, and then measure with your measuring tape. The example would be a 42 unit rack. It can house up to 42 rack units of equipment, and that is how we kind of think about rack units in general. So a 42 unit rack can house up to 42 rack units of equipment. Then there's the mounting option. So there's the 2-post racks, and then there's the 4-post racks. So the 2-post is each vertical post that you saw. So what we were looking at with the open racks were 4-post racks. So the 2-post is used for lightweight equipment like switches or patch panels or something like that. So nothing heavy, right? Physically lightweight. And then you have the 4-post rack, which provides stability for heavier equipment like servers, UPS units, so on and so forth. So I don't think I've seen a 2-post rack. I think everything that I've ever seen has been a 4-post rack, because it's also just good to have like extra stability just in case there's an earthquake or something. You don't want something to just fall and break, and because these things can be expensive. So the actual switches and the equipment themselves can be expensive. The racks aren't really that expensive. And you can always literally just build your own racks as well if you want to customize, especially if we're talking about the open panels, the open rack panels. But for the most part, I would say just get a 4-post one, unless it's like a really, really just you have one thing that you want to mount onto it, or just maybe 2 or 3 things, and it's like really solid. It's not aluminum, it's like steel, something like. But for the most part, I always just err on the side of caution, and I'd say just use something that's super stable, super strong, in case there's an earthquake or something like that. Nothing will drop these things from their rack, the mount racks. The rack mounts. Yeah, rack mounts. So being OCD and like being overly organized is actually like really good in this kind of an environment. It can be overwhelming if you really do like have OCD, because as you saw, like some of those wires can be really crazy, especially during setup. But if you are super organized, then you will do extremely well in this kind of a task. So it's a lot of it is common sense. So, leave space between the devices for proper airflow so that the heat from each device doesn't overlap. And if they're super connected to each other, then they're going to overheat each other. Like the heat from one is going to expand the other one, and vice versa. And use blanking panels to optimize cooling and prevent hotspots. Same thing, right? So space, hotspots, organization of wires, using some of the other tools that I'm going to share with you. All of those things are just, they're common sense and they're really good practices. And if you are unorganized, this is not the job for you. This is for somebody who plans in advance and it likes to be organized and likes making things look pretty, because in this specific conversation, things looking pretty is actually really good, and things being organized is excellent. For this specific conversation, those things are, I would say, they're necessary. They're like mandatory. A real world case would be deploying a 42 unit enclosed rack in a data center to organize servers, switches, and storage equipment while maintaining physical security. Why? Because it's enclosed and it's locked. And it's a 42 unit, which means it's definitely over 4 feet, because 42 times 1.75. So let me just do that real quick on my phone here. So 42 times 1.75 gives us a 73.5 inch rack. And so that ends up being a 6-foot rack, like 6.1 feet. So it's a pretty sizable rack, enclosed rack that's inside the data center. So that's just, one particular use case. There are so many different versions of these things. And if you go through Google Images, you will find so many different pictures of really crazy network rooms that are just, massive. Like I'm going to actually try to find an AWS server room, just so you can kind of see what it looks. It's a warehouse for the most part, probably, but I just want you to see what it looks like. So this is one image of an Amazon server room. This is actually a thumbnail from a YouTube video, so you can go watch this video just to get an idea of what the Amazon server rooms look like. And this is racks as far as the eye can see, and this is one side of the server room. So if you go down this hallway, this path that we see right here, and then make a right at the end, you'll probably see another entire section that looks just like this. So I think like in any given location, they have something like 450,000 servers, which is insane to think about. It's hard to even wrap your mind around it. But of course, there's the servers themselves, there's the actual wiring that goes into it, there's the cooling systems that we can see right here. There's a lot that goes into a server room or a warehouse. This is better, a server warehouse for a company like Amazon. This is a massive, massive, massive location. There's another one, and this one just looks freaking amazing. I love the way that this looks. Super clean, super organized. The lighting is just futuristic, and it drives me freaking crazy how beautiful this room looks. And I mean, look at how beautiful this is. This is just so freaking nice. I know I'm nerding out, but I just kind of want to show you what the big boys are doing out there, you know, compared to the initial images that we saw at the very beginning. If you wanted to work at a place like Amazon, or if you wanted to set up something like this, I mean, God, it would be amazing. I would love to see what it's like to go through the setup of this, and what it was like before and after, the before and after of this, and that whole the time lapse video of what they did. I'm probably gonna end up watching the YouTube video myself all over again just to make sure. But it's a very, very cool video, so that you can just kind of wrap your head around it. And then looking at the warehouses for their fulfillment, for fulfillment by Amazon FBA, that's also really interesting to see, because they have so many robots that they use, and it's just a really I mean, it's a reason why Amazon is as massive of a company as they are. So yeah, these are just a couple of examples, just so you can really see what it's like for a server room to be really properly set up and freaking massive. Cabling management, I think, is the hardest part of setting up a room, because it can get overwhelming very quickly. I would say starting by segments, or like starting in segments, starting with one machine, connecting it, organizing all of the cables, making sure you're good, and then move to the next one, connect it, organize all the cables, and then once you have a section, you organize all of the cables for that section before you move on to the next section. And that's the best way to be able to do this. Proper cabling prevents signal interference, it simplifies troubleshooting, and it enhances the scalability. And this piece right here, the simplifying of the troubleshooting, that's like my nightmare, where it's like, if you have the room set up and then now you need to go troubleshoot something and you can't find the problem because it's so disorganized, that drives me crazy. It's like terrifying to think about. And then going through just having to fix somebody else's improper setup is another nightmare, where like you get hired, which is why I don't want to go into networking. Like, I don't want to be a network engineer. They do get paid fairly well, and they deserve to get paid really well, but I'd rather be on the programming and cybersecurity and pen testing side of things, because those guys also get paid really well. So, and it's just it's a little bit easier on my anxiety and on my OCD. But you know, simplifying the troubleshooting it starts with really good setup, so that everything is organized and you know how to track back and reverse engineer where the problem is. So cabling is the biggest part of it. Like, I really feel like cabling is the most important part of setting up these physical devices, because it gets so hectic. So anyways, key practices here. So we have the cable types and the standards. So the twisted pair, we've already talked about all these guys. So Cat 5, Cat 6, 6A, 8, whatever. These are used for Ethernet connections. Cat 6 and 6A support higher speeds and reduce crosstalk. Then we have the fiber optic cables that are suitable for high speed, long distance communication. And there's the single mode, which is long distance, and multi-mode, which is short distance. So these are the types of cables, for the most part, that you're going to end up seeing. And then there's the cable management part of it, the actual tools to help you manage those cables. So cable trays and ladders, and these are for routing tables across racks and ceilings. And then we have the patch panels that centralize cable connections for organized termination. And then you have the Velcro ties and cable labels and all of that stuff that just helps you organize and helps you know what you're looking at when you go through troubleshooting, and identify which segments of the network you're looking at. So they secure and identify cables. So Velcro ties are for security, and cable labels identify the cables. Now what we're looking at over here is a cable tray that allows you to, I think this is a patch panel. I want to say it's like a cable tray / patch panel. And so it has the input and then the output. So what this does is that you essentially, these are, it could be either way, right? So these, I would say, are the input cables that are going in, and then on the opposite side of it, the same type of cable comes out and just goes to connect to either the segment in the building or to another device that is supposed to connect to. And what happens is that usually what you will see on the front end of the machines, and I will again try to find an image for you, but the ones that we see on the front end, these blue wires are much shorter because they just need to fold down and connect to the device that's right below it, or something similar to that. So it doesn't make sense to have a 10-foot wire if you're just trying to connect two devices that are literally an inch away from each other or 2 inches away from each other. So what happens is that you use these much shorter cables to connect those devices on the front end so that you could easily manage them. And then the longer cables on the back end will actually go and leave from that given device and go to somewhere in the building. So it gets dragged out of that location and it just gets kind of pulled out. So this is what, and I'll just try to find you an image real quick that kind of helps you make sense of that. Okay, so this was the specific image that I was actually trying to identify, and unfortunately it's not a very high quality image, so we have to kind of rely on it with the little fogginess that it has right here. But you can actually see that these white wires are connecting from the top one to the lower one, from this one to this one, and so on and so forth. And these are really short wires because they're going to connect these various segments to each other. And then you see on the back end, you have these super long wires that are coming out, and then they're going to leave this room and go to different parts of the building. So this is a really perfect example of what I was just trying to talk about. There's freaking nightmare images here that I just anxiety through the freaking roof when I see some of these images. I'm like, no way that somebody did this. Like, why would you do that? This is a really good image to show you what the back end of it looks like. So the wires that come out and how you can basically organize them. These are all Velcro ties that we're looking at here. And these all just come down. And really, this looks like, this is why, quantum computing and all these things end up impressing so many people. And it even impresses, the biology people, because when you actually see a really organized cabling structure, especially like this, it kind of looks like this is the spinal column of the human being, and these are just nerve endings that are connecting to the spinal column. So this is it's like really, really amazing when you see how a really big, this is actually another excellent image that kind of resembles that. This just looks like it could be the spinal column of something, or it could be like a robot's spine, let's say, and it has all of the wires that are coming out of it, and these are all veins. It's very, very fascinating to me. Stuff like this is very fascinating. And this is a super unhealthy person that all of their freaking veins are just really destroyed. It's, oh my god, it's terrifying. These images are like scary, bro. This is what the front end of this thing looks like. This is what the back end of it looks like. The back end obviously needs to be like super, or I think this is like a before and after. Yeah, this is a before and after. So this is what they were doing before, right? So they had all of the long wires on the front, and the long wires were connecting to each other. And what they did was they started using super short wiring to connect these front segments together. And that's actually a perfect example of what I was trying to talk about earlier. And this is how powerful organization is. This is the same exact connection. It's literally connected to the wall, and you can see right here, right? So same thing, connected to the wall, except on this side, all they did was, like, the biggest difference that whoever was organizing this, the biggest change that they made was he just used shorter wires for the front end connection, and then made sure that everything was dragged out cleanly from the back end. And that's it. It's not overly complicated if you plan and if you organize. And that's the piece that's just like, man, that's so beautiful. Look at this before and after. It's amazing. It's like a 600-pound person that got into crazy shape, and now they have six-pack abs and all of that stuff. Cabling design, as you've seen through so many images by now, needs to be structured. You need to separate power and data cables to reduce magnetic interference, to reduce heat, use color-coded cables for different functions, so red for power, blue for data, or to separate segments or separate rooms, right? Just depending on how big your network is and what the purposes are. So structuring your cabling design and just making sure that the planning phase of this is organized so that as you go through implementation, it's just easier to implement everything. Which brings us to power. So considering the various power sources and formats of providing power to your various network devices and the physical setup. So the uninterrupted power supply is a big deal. So this connects to not just the actual power cables and the power supply of the building, but backup power in case for whatever reason the grid goes down and you actually don't have power coming to you from the electric company. So the uninterrupted power supply is critical for network uptime and equipment safety. And then the uninterruptible power supply, which is UPS, it provides a backup power during outages. And this is something like a generator, right? Protects equipment from voltage spikes and surges. And it has the various types of standby, the line interactive, and online UPS systems. And these are all as a backup power. So these are like redundant power sources. And then we have the power distribution unit that distributes power to multiple devices in a rack. And you could have the basic PDU, which is for simple power distribution, or you can have a smart PDU that includes monitoring and remote management features so you can actually see what's going on with the power uses of the various devices in the rack, how the power is actually being distributed. You get charts and you get updates and monitoring data and so on and so forth. So obviously, Amazon or like a really big company like Amazon would be using smart power power distribution units, and they probably have their own power supply grids that are coming in. And I just wouldn't be surprised if they had their security or not security solar panels and a variety of different types of power sources feeding their infrastructure so that they're not just relying on the grid, the electric company to provide them power. Of course, we are going to go through the concept of redundancy here as well. So dual power supplies for critical equipment, so redundant power paths to avoid single points of failure, and having environmental monitoring as well, which sensors for temperature, humidity, power usage. If you're in an environment, which I mean, if you're a company like Amazon or Google Cloud or something like that, and you are building your warehouses, I would hope that you do research in advance that you're not in an environment that is extremely humid or gets really, really hot or is sitting on a earthquake fault line, like just so many different factors that you would have to consider for the environment of the thing. And then just monitoring all of that stuff for, again, the humidity, temperature, power usage, and then integrating it to the power distribution unit or having a separate monitoring system that could be completely up to you or up to the company. And then as somebody who would be a network engineer or network administrator, you would be the person monitoring these things, because most likely the setup is going to be done for you and your job will be to just make sure that you can monitor. Then there's the cooling system, which prevents overheating of equipment, and it could be the hot aisle, cold aisle configuration, and rack-mounted fans. And I mean, again, super complex cooling systems. Probably commercial air conditioners will be used for massive warehouses like the one that Amazon or Google have. So cooling systems is very, very important because these devices can get very hot very quickly and they can generate very, very many degrees of heat. So to keep that room cool, you would need an industrial air conditioning unit, or maybe even turn the entire building. Like I used to have a client when I was in banking that they would create commercial refrigerators for companies like Costco or Ralph's, and they would turn a warehouse into a refrigerator. So the massive cooling systems that are being installed, and then they would probably do something like that. I would presume they would do something like that for a warehouse that has 450,000 freaking servers in it, right? So the use case here that we would see in the real world would be deploying an online power system and the smart power distribution unit in a data center to provide uninterrupted power and monitor power consumption remotely. So this is the uninterrupted power supply, and then we have the power distribution unit for the data center to provide uninterrupted power and monitor the power consumption remotely. Scenario time for physical installation. So scenario 1 would be organizing the network equipment. And the problem is that the server room lacks organization, as we saw in some of those images, and it causes difficulty in troubleshooting, obviously. So you install a 4-post rack system with labeled patch panels, and you go through all the freaking cables and organize all of them and Velcro tie them together. Scenario 2 would be to prevent downtime during power outages. So the problem is that the network equipment loses power during electrical outages. So you want to deploy an online uninterruptible power supply with sufficient capacity to power critical devices. Scenario 3 would be optimizing cooling in a data center. And the problem is that the equipment overheats due to poor airflow. So you want to employ the hot aisle, cold aisle configurations and use blanking panels to direct the airflow. And this is actually, I think, the perfect time to look at the hot aisle, cold aisle concept. And this is a really good example. It's a great visual for this. So the cold aisles are this aisle and this aisle. And the air that is coming for those aisles is coming from these air conditioning units that are against the wall. And it's going through the floor and it's coming up. And these aisles are serving as the cold aisles. So they're being fed cold air to keep the devices that are in these blue boxes cool. Now, these devices emit hot air, and it usually comes from the back of the devices. So you can see that this is the front end of this blue box, and this is the front end of this blue box, and this is where the admins come to manage these things, and the engineers. And so these portions right here would end up being the back end. This room right here ends up having the back end of these two aisles. And the heat that is emitted from this comes out of the ceiling and goes out, and then it feeds into the cooling systems, right? And so the cooling systems, usually the way that it works is that the cooling systems also give off hot air as well. So you need to have an external segment for just the heat leaving the room. So this could actually be, a part of this could be that, you know, part of these two panels that we see, these two segments that we see on the wall, a part of it could be that the cold air is coming in from the bottom and being fed into this room itself. And then the other part of it could be that the hot air that goes up from here goes through here and it leaves this room entirely, including the hot air that's going to be emitted from the cooling units themselves. So this is a really great way to display the flow of the temperature inside of the room and how these things actually are managed. And so if you had this in a much larger environment, then you would have several aisles that are separated like this. So the next aisle in front of this one right here would be literally identical to this, where the next aisle over would have something like that, where the cool side would be here. And so this would end up being the cool aisle. And then there would be this segment behind them. So I can find you another picture that actually displays this. And this is the other image. So hopefully this will kind of, it's all pixelated. I want you to see something that's a little bit easier to look at, because it's not freaking pixelated. I don't know why all these images are pixelated. That's insane. That doesn't even make sense. So let's see this one. Okay, this one is not pixelated. So this is now multiple aisles of this, right? So we have the hot aisle, which is this portion. You have the cool aisle, which is this portion. And you can see that the cold air is coming through the ground. and then the hot air is leaving, and it's typically going outside of whatever the insulation or whatever the segments of the room are that are designed to be able to capture it. And then so you have this cold aisle, there's a hot aisle, and then this section has its cold aisle, and then there's a hot aisle, and then next to that one there's going to be a cold aisle and then a hot aisle. And that's how it works. And the cold aisle has the air conditioning usually come from the bottom because heat rises, and so as we feed the air conditioning from the bottom, it keeps this section cold, and then the heat that comes out of these things, we have to organize the room in a way that there is insulation. So there could be vents on the ceiling right here that make sure that the hot air immediately leaves from this little segment, or there could be a unit on the wall that allows to filter that hot air out. So it just depends on the setup of the room, but this is the hot aisle, cold aisle concept. And for scenario 4, the scaling power delivery for growth. So the problem is that the company plans to add more servers, but they lack sufficient power distribution. So you want to install a smart power distribution unit for additional outlets and monitor power usage as the capacity increases. Which brings us to our practice questions for the physical installations. So what does the U in rack unit represent? So this is a unit, right? It's the measurement. And I already see it right here. So it's a height of a rack mountable device, and it's 1.75 inches per U. And that would be our answer. What type of rack is best suited for environments where physical security, oh, I accidentally clicked the button, damn it. Where physical security and airflow control are required. So you need physical security and you also need airflow control, and it's obviously the enclosed rack. You either have an open frame rack or an enclosed rack. The 2-post or the 4-post are the types of racks that we have, it goes specifically into it. And I can't imagine that you would have a 2-post enclosed rack. So you would only be able to have a 4-post enclosed rack. So the 2-post and the 4-post concepts are more relevant to the open frame racks. And then in this particular question, we're talking about physical security being a thing. So obviously it's enclosed rack. I already pressed the button, so that was like a gimme, but that we just want to work through the logic of the answer. So what is the purpose of a patch panel in structured cabling? So it provides backup power during outages. That's not true. Routes cables neatly and centralized connection. That's great. Cool network devices to prevent overheating. No. Prevent signal interference with fiber cables. Potentially, but it's routing cables neatly and centralizing connections. Which type of cable is ideal for high-speed, long-distance communication? And the Cat5e is the twisted cable, so that's not it. Coaxial cable is definitely not it either. Single mode fiber optic or multi-mode fiber optic. So we want high-speed, long-distance communication. That would be our single mode fiber optic. What is the primary role of a power distribution unit? So provide backup power during outages, distribute power to multiple devices in a rack, monitor environmental conditions in the data center, reduce electromagnetic interference. So it's not this one, and it's not monitoring conditions in environmental conditions in the data center. That would be a specific environmental monitor. It is for distributing power to multiple services in a rack, as the name implies, power distribution unit. Providing backup power is our uninterruptible power system, so the UPS, right? So we have the distributing power to multiple devices. What is a key benefit of using Velcro ties for cable management? Provides better electrical insulation, prevents cables from overheating, allows for easy adjustment and reorganization, ensures cables are permanently secured. So it's not permanently secured because it's Velcro. So allows for easy adjustment and reorganization. That's pretty good. Prevents cables from overheating. I mean, not really. Provides cables better electrical insulation. No. So easy adjustment and reorganization. Which component is used to monitor power usage and environmental conditions in a rack system? So power usage and environmental conditions, and it's a monitor. So it could be a smart PDU, which is the power distribution unit. Patch panel, it doesn't really do that. 2-post rack has nothing to do with it. Line interactive uninterruptible power system is more like a redundant power system. So the only thing I can think of would be the smart PDU. Very good. What configuration helps optimize cooling in a data center? So placing devices randomly in racks? No. Using hot aisle, cold aisle? We just talked about that, so that has to be it. Disabling rack-mounted fans? Disabling rack-mounted fans? What? Okay. Mixing power and data cables in trays? No. So no, because this will be electromagnetic interference. The rack-mounted fans have to be turned on. That's ridiculous. And these are the fans that actually feed the hot air into the hot aisle, and then the cold aisle is where the air conditioning power comes in, or the air conditioning temperature comes in. Which type of uninterruptible power source provides continuous power without switching during an outage? So standby UPS, line interactive UPS, online UPS, hybrid UPS. I want to say it's the standby. So it's the standby UPS or the line interactive. I think it's the standby. Let's see. I'm going to say standby. Oh, it's the online UPS. Oh my God, I was so off. Okay, so standby UPS, line interactive UPS, and online UPS. We need to look into these to get better explanations for these. Okay, so the standby UPS is an offline UPS. It's the simplest and most affordable. Power flows directly from the utility grid to the equipment, and the UPS acts as a surge protector. The power is if the power is lost. So when the power is lost, the UPS switches to battery power, providing a brief period of backup time. It's cost effective, good for basic protection against minor power fluctuations and short outages. It offers limited power conditioning and can have a noticeable switching time when transitioning to battery power, which may disrupt sensitive equipment. Line interactive UPS is more advanced than standby. The power flows through a voltage regulator, which adjusts for minor voltage fluctuations. Power outage switches to battery power when the utility power fails. The pros are that it provides better voltage regulation than the standby UPS, and it offers some protection against the power surges and sags. It may not provide the same level of power, however, conditioning as an online UPS. And so that brings us to the online UPS, which is the double conversion UPS, and it's the most expansive, most advanced and expensive. And the utility power is first converted to DC power, then back to AC power. And this provides continuous power conditioning, isolating the connected equipment from any power disturbances, and seamless transition to battery power as the UPS continues to generate clean AC power. The pros are that it provides the highest level of power conditioning and protection against power disturbances, and it ensures uninterrupted power supply to critical equipment. Now, the cons are that it's more expensive than other types, obviously, and it actually generates more heat, which is understandable. So now, knowing this, if we go back to our practice question here, and the question says, which type of UPS provides continuous power without switching during an outage? And so both of these guys, the standby and the line interactive, actually switch during the power outage. This is continuous power without switching during an outage. So that actually makes sense. What is the primary reason for separating power cables from data cables? To simplify troubleshooting, to prevent electromagnetic interference, to improve the speed of data transmission, to make cables easier to label. And I mean, by just using different coloring, you can make sure that they're easier to label. To improve the speed of data transmission, not really, but to prevent electromagnetic interference would be the answer. And that's it. We are now actually moving on to Section 3, Chapter 3, Organizational Processes. To get access to the Network Plus notes, as well as the mock exams and the practice question slides, join the Hackaholics Anonymous community. If you join as a cyber agent, cyber guardian, or cyber master, you'll get access to all of the notes, the mock exams, and practice question slides, as well as many other perks that are available to Hackaholics Anonymous members, like Python automations and exclusive content, as well as monthly live streams with me. And to join, you can click the link in the description below, or you can go to our homepage and click the join button there, or you can simply go to youtube.com/@HankHacksHackers/join, and you'll be able to join Hackaholics Anonymous. Now let's get back to the Network Plus training.